In this lesson, we're going to solve quadratic equations by graphing. A quadratic equation can be solved by graphing the corresponding quadratic function. The standard form of a quadratic equation is 0 equals ax squared plus bx plus c. The roots of a quadratic equation are the x-intercepts of the graph of the corresponding quadratic function. They are also the zeros of the corresponding quadratic function. So remember when we're going into our graphing calculators and we solve for our x-intercepts, we're actually going second trace 0. That's because those two words are interchangeable. Looking for your x-intercepts is looking for your zeros. For any quadratic equation, there can be 0, 1, or 2 real roots. You might have remembered me telling you this once before. This is because a parabola can intersect the x-axis in 0, 1, or 2 places. Okay, so if we look at these three possibilities, your quadratic could be floating, right? Like you can have it sitting something like that, where it's not actually touching. It could be anywhere, right? It could be there. It could be in this quadrant. If it's in the bottom quadrant and it has none, it would be sitting down here, or it would be sitting down here, right? So wherever it happens to be, it's up off of the x-axis, okay? And so that would be no roots. In other words, zeros, in other words, x-intercepts. So when we're talking about solving quadratic equations, what we're doing is we're finding those zeros. You can see here, we're setting our y, which is normally y equals ax squared plus bx plus c. We're setting our y equal to 0, so we can actually solve those x values. Now, there's possibility of one root. How can you get only one root? Well, that's when your vertex is actually sitting on the x-axis. Okay, so something along the lines of this, where it's actually sitting right there and your vertex is sitting on the axis. Again, that can happen in any of these instances, right? In any of these 4 quadrants, you can have your graph sitting on the axis. Okay, those are all different possibilities there. So that would be one root, 1, 0, 1 x-intercept, however you want to call that. And then the 2, that's what you're seeing in most of the examples we've done so far, because I wanted you to practice finding the x-intercepts. But that would just be something like this, where you can see that it's going through in 2 places. You can have it like this, right? Any of those would work, where your graph is going through the x-axis in 2 different places. Okay, so 3 possibilities. So if you're doing this and you only get one root or even no roots, then this is why that might be. Let's take a look at the first example. It says solve each equation by graphing the corresponding functions and determining the zeros. So that is the solution. When we say solve, it means find the roots of the function, determine the zeros. Let's take a look at this first one. So pull out my graphing calculator, clear out what I have in here from before, and put in the 2x squared minus 5x, subtract 3. If we go zoom 6, we can see our parabola there. So let's draw a quick sketch of that. There we go. Here's my x and my y. And we're going to find out where exactly that's going through. Here we're not worried about or concerned about the vertex at all. We just want to know what those zeros are. And in this situation we have 2. So second trace, you're going to go to 2, which is 0, left bound, right bound, enter. That's at negative 0.5 and 0. And remember, when you're graphing this, you just have to put the negative 0.5 on there. You don't need to put the other coordinate. Let's get the other x-intercept. So we're going through that again, second trace 0. But now you're moving the cursor left bound here, right bound here. And our 0 there is at 3. Now, I'm glad this happened. You can see the y is 1e negative 12. What does that mean? That means 1 times 10 to the negative 12, which is essentially 0. It is negligible, right? Like, that is so small. It's so close to 0. We can count that as 0 and put that in as a 3. If you went back and tested that, went second trace value and put in an x value of 3, it would actually give you that 0. So you can always go back and double check and be like, whoa, why did that give that to me? And you can see that that 1 times 10 to the negative 12 is in fact 0. So there we go. So state your roots, put them on your on your sketch, and actually state them as well. So your roots are 0.5 negative and 3. So solving that quadratic by graphing means stating those roots and drawing a sketch. At this point, you probably want to hit pause on the video and try B on your own. Like, don't just follow the video through, but try it on your own and see how you do, and then go ahead and press play, and I'll have the answer sitting there for you. Okay? So hopefully you did this and you got the same answers as me, 0 and 2.25. And you can see I just drew my sketch a bit bigger. I stretched it out with my window so that I can have a better view of what was going on. And then I did that with my sketch as well. Let's take a look at example 2. Rearranging quadratic equations. It says rearrange the following quadratic equations into standard form. Reason being is we can't do what we did in example 1 until your equations are in the format where we can actually put them into our graphing calculator. So you're doing a bit of algebra here, and that's really good review. Okay? So remembering when you have a coefficient here like the x, you'll want to distribute. So we've got 7x minus 2x squared is equal to x squared plus 1. Now you want to gather all of your values on one side to be left with 0 on the other side, very much like we did in our previous examples here. So in my case here, I'm going to move everything to the left. So subtract the x squared and combine it with my other x squared stuff, creating a 0 pair here. So I've got 7x minus 3x squared is equal to 1. I want that 1 gone, so create a 0 pair by subtracting 1. I have nothing to combine with, which is fine. I'm left with 0 on this side, and I've got 7x minus 3x squared minus 1. That's not quite in the format we want yet. We want ax squared plus bx plus c equals to 0 to be our format. So I'm going to move my negative 3x squared. Don't forget that this is all one piece. You take the sign that's in front of the coefficient. So negative 3x squared plus 7x minus 1 is equal to 0. And now that's simplified the way we want it to do it. We want it to be in order to solve it. Let's try B. Again, we've got coefficients, distribute, distribute. So we've got 4x squared plus 12x is equal to 12x plus 9. Get rid of the 12x from this side, and I'll do that to the other side as well. Those are gone, so I've got 4x squared. Oh, that actually goes away as well, is equal to 9. Get rid of the 9 from both sides, and I have 4x squared minus 9 is equal to 0. Now, ask yourself, is that in the format ax squared plus bx plus c equals 0? Sure it is. Just because you don't have one of the terms because your coefficient is 0 doesn't matter. You're still writing it in that format. You can still solve that like you would solve any of the other ones. Let's take a look at example 3. Solving a quadratic equation in non-standard form. So non-standard form, exactly what we were doing in example 2. You're going to put it into standard form, and then you could do what we did before and solve by finding the roots. They actually say verify your answers as well, so we'll see how we can do that. So taking a look at this one, I see I have to do some distribution. Got 3x squared minus 6x plus 5 is equal to 8x minus 2x squared. Now let's move everything over, subtract the 8x to combine with my x stuff on the other side. I've got 3x squared minus 14x plus 5 is equal to negative 2x squared. In order to create a zero pair here, add 2x squared. So I've got 5x squared minus 14x plus 5 is equal to 0. And that's actually in our standard form right away. We don't have to rearrange that. So now we have that, we can go ahead and use our graphing calculator to graph it and find our zeros. And again, at any point, you can hit pause on the video, try it on your own, and then check back in, right? Let's go ahead and put that in. We've got 5x squared, subtract 14x plus 5. Now don't put that equals 0 business because really it's equals y, and we're setting y equal to 0, so we're solving and getting those roots. So let's hit zoom 6 and see what happens. You can anticipate, right, what might happen here. So we've got a minimum. Why does it make sense that we have a minimum? Because our coefficient is positive, and we need to find those two zeros. You might want to stretch your graph out so it's easier to see. We go second, trace, find our zeros, left bound, whoops, enter, right bound, enter, enter again, and that's at 0.42. Let's get our other one, second trace, 0, move over, left bound, right bound, enter again, and there we've got 2.38. Okay, let's draw the sketch and state our zeros, and then that example's done. So I've got my graph here. Whoops, straighter graph, not like that. This point here was 0.42. This point here was 2.38, and we can just state those as zeros or roots or x-intercepts, 0.42 and 2.38. And now you've solved that quadratic equation. Let's take a look at example 4. That's the last example for this lesson. Verifying solutions to a quadratic equation. Oh, and it actually asked us to do that here too. How would you verify those? You can plug them back in. Okay, you can plug in the 0.42 in your x and try it out, and it should give you 0 or very close to 0 because we did some rounding, and then the 2.38, you could go ahead and do that as well. Alright, so I always like when we have these questions where they're modeling something that actually is represented by a quadratic function, because you can kind of relate to them a little bit better. It says the flight time for a long-distance water ski jumper depends on the initial velocity of the jump and the angle of the ramp. For one particular jump, the ramp has a vertical height of 5 meters above water level. The height of the ski jumper in flight, h of t, or h as a function of t, in meters over time, t in seconds, can be modeled by the following function. How long does the water ski jumper hold his flight pose? When is the ski jumper 21 meters above the ground? And what height is the ski jumper 3 seconds after he takes off? So again, this is another wonderful example where you can hit pause on the video, try it on your own. I think you have all the tools you need right now in order to be successful in doing this example. And then press play and see if you're getting the same answers, and if not, you'll see why. Okay, my first job I'm going to do is put this in my graphing calculator. I've got 5 plus 24.46. They say t. I'm going to do x minus 4.9 x squared. And you'll see it's in standard form, but backwards order. Does it really matter? No, as long as everything is equal to 0. But when I ask you to put it in standard form, make sure you're putting in that descending order of your power. So ax squared plus bx plus c. Will this work when I put it in the graphing calculator? It sure will. Okay, so let's go ahead and hit zoom 6. And that's okay, but not great. You can't see the vertex, and because this is a problem where the negative quadrants don't really count, I'm seeing more than what I need. So let's change our window around. I'm going to go -2. Remember, you can go to 0. The reason why I go -2 is just so that if I have to do any tracing around there, I can see what's happening. So that looks good. I just got to figure out this vertex business. And let's change that. Y max. Let's try 20. Let's see how that goes. Well, that's not nearly high enough. So choose another value you want to make that. Let's try 50. Okay, so now we can see the graph and see what's going on. Now remember, when they're saying, right, solve the quadratic function, they're just talking about the x-intercepts. But in this problem, they're saying, how long is the water ski jumper? How long does this water ski jumper hold his flight pose? I was going to say, how long is the flight, which is basically the same thing. But when the ski jumper holds the pose, it's from the start to the end, right? So let's draw a sketch. It'll help us out. And label the key pieces of information on here. Now, it's tempting to do this with your sketch, right? Now, this is a problem if you sketched it like that. Why? First of all, you can look at your graph, but second of all, you can see that the ramp has a vertical height of 5 meters above the water level. That means that just the jumper does not start at 0. The jumper starts at 5 meters. And go back and have a closer look at your graph, and you can see that, right? You can see that that's there. Not at 0, 0, right? If we extended our window back out and made my y min back to -10, you can see, right? It goes past and through that point. So we're actually starting up here and then coming back down. And for some reason they made it wider, sorry. Okay, so here's my y, here's my x. In this case, they're talking about h and t, so if you wanted to change that this is your height and this is your time, that's fine as well. And we now know that that's 5. Double check that in your graphing calculator. Second trace value, put in the value of 0, and you can see, yes, that is indeed 5. So what about the end point? How do we figure out what this value is, which is essentially what they're asking us to figure out? Second trace 0, your left bound, and enter. Oh, went too far. Let's try this again. Enter. Right bound. Enter. Enter again. And that's 5.19. Okay. We can round that to 5.2. So for A, we could put that on our graph here. For A, it says how long does this water ski jumper hold its flight pose? And that is 5.2 seconds. So when you're answering these questions, 5.2 isn't enough. You need to put those units in there. When is the ski jumper 21 meters above the ground? Well, how would we do that? 21 meters is a height or a y value. So when you're doing a question like that, you're actually going to graph, I'm going to write this in here, graph the horizontal line. And by doing that, you can then find where it intersects. The parabola. And it's those points of intersection that will give you what you need. Okay, and you're going to use your second trace 5 once you've done that. So the value we're looking is 21 meters above the ground. So if I go into y equals, and put 21 here and trace, you should see that line. So you can see that the ski jumper is at 21 meters above the ground in two places, once on the way up and once on the way down. Where exactly? So second trace 5, intersect. Now see where my cursor is? It's going to go and find that point of intersection where it's closest to. So if I want the first one, before I hit enter on first curve, I actually need to put it closer to that other point I want. Now I can go enter, 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 and it gives me the intersection of 0.77 seconds and 21. I'm going to just make note of that. So it's at 0.77 seconds, and there's another one. So you need to look at your graph and see, is there one point or is there 2 point of intersections? 5 again, but now I'm close to that one that I've already done, so you've got to move the cursor over and find out what that other one is. Enter, 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 and there we've got at 4.2 seconds. We used 2 decimal places before, so I'll use 2 decimal places here, 4.22 seconds. Okay. The last question, what height is the ski jumper 3 seconds after he takes off? So in this case, you're using second trace value because they're giving us an x value or a time value. Second trace value, and you're going to put in a value of x equals 3 in your calculator and get the corresponding height. So second trace value 3, and the corresponding height for 3 seconds is 34.28 meters. So we get y value is 34.28, and we can say that means that's a height of 34.28 meters. So again, make sure you've got your units and all of your stated answers. Alright, that's it for today's lesson. Thanks for joining me.